how databases are broken by giving them too much data, not enough hardware. But first, let me quickly introduce myself. I'm Jerven Bolleman. I work for an Assistant Institute of Bioinformatics. I do the UniProt RDF, also the UniProt website and other things. I'm going to skip that entire part of the talk because we don't have enough time. So I'm just going to give a quick summary of why Sparkle. Biologists don't really care about Sparkle. They say, give me a better pipette, we're happy, go away with all that IT stuff. Our world hackers say, well, it doesn't really matter, we can do all this stuff with our existing technology, and I reply to them, well, yes, you can do it with clay tablets as well. All that changes is the number of slaves, PhD students you require to get the answer. Technologically, if you have Turing complete or equivalent language, it doesn't really change, but in financially and social terms, Sparkle really beats the alternatives. And that's because in practice you can Sparkle with variable performance basically against anything, against relational databases with system mapping, programs with the SADI framework, the many triple stores that you have existing, but even with small converters against existing flat file formats with minimal translators, against comma-separated spreadsheets kind of data using different tools. So you have one query language that can access data in many different ways to store it. So it kind of separates for the first time the query language and the storage model, which is very different from, for example, Cypher, which is tightly bound to the Neo4j storage model, or some of the SQL languages, where again it's very much bound to the storage model. It's also very different from web APIs, REST APIs, where again the query language is modeled against a single implementation. Sparkle, being so flexible, given performance issues, however, also gives a lot of standards compliance, and that standard compliance is really a driver for aggregate performance in the community. So a little bit about our data. UniProt RDF. I'll go maybe a bit quick. So we've been doing this RDF for a reasonably long time. My predecessor in 2006 released his first beta of UniProt RDF. Had 80 million triples. That was in 2006. Today I counted it was 12 billion, so a significant growth in that period. But what's very different from most other organizations, we release it every 4 weeks. So every 4 weeks you get a new release, new data, new model sometimes. We really maintain it like we do all our other flat file formats, XML formats, any kind of interchange. They are compatible, so what is in our RDF is in our flat file, what is in our flat file is in our RDF. We don't lose any information. And critically, our benchmarking side is our data model changes over time. So because we were one of the first big data sets to be publicly released, on the FTP side you could go down and download it. People have used it for benchmarking. There's quite a lot of papers out there that says, we loaded UniProt and it worked pretty quickly. The problem is for benchmarking purposes, UniProt really changes. So we had a person who published a paper saying, look, you can compute the OWL closure over the UniProt graph in 6 hours. And our predecessor, as other people, did it and it took them 4 weeks. Unfortunately, in between those two papers, we changed all same answer statements into Scott's exact match statements. So the complete benchmark had really drastically changed, and had major performance changes. The way that we do with feature positions on the proteins has completely changed. We get more structure because, well, we're a database that has been around for 25 years, so we have a lot of text, specialist human readable, not average human readable text, and that text changed into templates, and those templates then get changed from strings into bigger triple bunches, and that changes over time. We were having a lot of blank nodes or local document nodes. Many of those have been replaced by distinct identifiers, quite large ones, because we use SHA-284 checksum for those. So completely changing what the URIs look like, and that really impacts things like compressibility, because instead of a regularly monotonically increasing identifier, you now have 600 bytes, of which 300 of them are completely random, so compressibility really changes. And another change which is coming for the import subset of the database is we are currently have about 40% of the database is replication plots, and in 2 months all the replication plots are going to be removed, and our modeling there is completely changed to really make nodes and entities of previously existing documents, even if they're no longer publicly URI or given one. So that kind of data model changes mean you can't just use a raw UniProt release and say, we wait at the benchmark and just say, we'll deal and see how it goes, because it really changes drastically over time. Also, over size. Our triples grow about 63% in a year. That's unique triples. Ununique triples grow a little bit quicker, not significantly so. 63% more data in a year is, a lot, and it means you can't compare results over time. The triples are actually quite nice, because RDF being set-based, if you repeat yourself, you will get merged, and that is actually a big difference. About 40% of our information in XML format is repetition, that is repeated from somewhere else. So you'll see that over time, our RDF files will get smaller compared to the other files, which is kind of one of our hopes. Also, things like, you might say, something is true for a protein in one species. On average, the same thing can be repeated for another 12 species. That's average. We get more and more high throughput papers, so you get some kind of sugar binding prediction on proteins, and that you then do for 400,000 proteins instead of one. And basically, so you get the same fact for different entities, that kind of thing gets replaced. Every protein belongs to a species. In the flat file and XML format, we have to repeat the entire lineage of that species, the entire species name. Well, in RDF, you don't have to do that. One time saying the relation is far enough. You don't have this kind of repetition. So that really changes the number of triples. And that really changes, again, performance compared to your existing technologies. One of the nice things is that, because it's completely standard, our experience with RDF has really changed over time. Because when we started in 2006, and I got into the group in 2008, 80 million triples took about a week to load in our own MySQL implementation. We had a bit of circle, and we might have returned results of the in 2014, in a very powerful server today, again, the 12 billion triples take for us a week to load on the source can definitely do it very much quicker. And it takes the same kind of time, 32 hours, into a key value store, similar hardware. But most significantly, Sparkle queries do return. They actually are usable. You can provide some really interesting analytics and programs. A little bit about the benchmarking. UniProt is significantly different from, for example, Bolleman and SP2 Bench, which are two of the larger or well-known benchmarks for RDF tools. UniProt has many graphs, those other two ones don't. UniProt has more than 164 types. Bolleman 19, SP2 Bench counted by hand is quickly 13. Object properties we have more than 50, and those have 25 to 20. And the data type properties in the SP2 Bench can quickly count from the paper, where we have 81. Also, the amount of variance we have in the predicate bindings, predicate statistics is extremely diverse, and also from subject to objects. So you have entities which are only present in one triple, and you have entities which are present in more than 2 billion triples. So you have very big divergence in how often certain entities appear, and it really changes how effective predicate statistics are in making good query findings. But for the benchmark issue, it's not all about analytics. SPBench and Bolleman are kind of the business intelligence kind of analytics approach. You load some data, do some business intelligence queries on it. But there are more problems you have. You have the graph queries, so more towards nearest neighbor, that kind of thing. But also online transactional processing. How does it hold on to that kind of performance? Or key value. And in Sparkle terms, you could say something like key value is more like describe queries. Or analytics is definitely the select types. The LDBC is the insert delete, the Sparkle kind of queries. And these don't really seem to be well covered with public data benchmarks that are out there. And what I'd like to see from Sling Data Benchmark Council is not just to say, well, this is the best analytics engine that I'm going to get, but it's actually also a decent LDB engine. So to really say, well, okay, I have a use case which is very analytical driven, so I make a selection. It's more important to perform well on that axis. If you're driving, a classical website or more record-based, you kind of describe more kind of key value kind of queries is essential because that's the main volume of queries. If you can use that to avoid many joins and have really great performance on that, that can be quite valuable. Because the analytics queries, well, I might be doing once a month and I don't really have to worry about them so often. Again, to really expose the full set of behaviors that can be driven from the Sparkle standards, to not just say, well, we'll just do more BI, but actually really drive the decision matrix for the entire solution space or problem space. And the same is true for graphs. We have path queries in Sparkle, but that's not enough. There are already some people who are doing different nearest neighbor and other graph algorithms with magic properties in their database. Are those covered? Can we figure out a way to say, well, that's a little bit more standardized and also more benchmarkable to compare to? But on the other hand, what's really nice about RDF and Sparkle is it's relatively cheap to benchmark all these different systems. I mean, UniProt, you have an STP site, you have 12 billion triples. You say to your vendor, say, well, can you load them? Yes, no. Okay, if you can load them, then it goes on to the next stage. Here's a bunch of queries. Can you run them X amount of time? Yes, no. And you can really make a very strong performance-driven comparison with relatively little investment. Compare it with even two SQL implementations. If you say, let's say, you want to make Oracle and IBM compete, right? So you say, well, I have Oracle in the database and it's not performing so well. So IBM, what is your DB2 doing? Or Teradata, how is your SQL doing? In practice, you hardly ever do this because the divergence in SQL dialects from what is actually written in applications from the standard basically means that you have to do the migration just to see if it's going to work. And then you don't even know yet if it's fast, so you'll never do that. But RDFs and Sparkle side, well, as long as you have no extensions used for your Sparkle, you just say, here's my triples, here's my queries, how quickly can you do it, and for what kind of money. So you, as a client, end user, it's really nice to actually be able to hold competitive, very strong benchmark on my use case, and not only have to hope that the TPCH results are somewhat representative for how I actually work with it. Because if you look at some of these, you get a $1 million SAN, half a petabyte of disks, you use 40 megabytes of it because you all short stroke the old efficient hard disks. That kind of TPCH benchmarks wasn't very useful for me to decide if I was going to use Oracle or DB2. That was just nice to see in the magazine, not really a decision supporter for me in my day-to-day work. So the benchmark should really just help us make choices, not just on one section, but on different sections. I basically would like to see 4 winners for one benchmark. Different areas, really like that, like this is what good performance is for this specific problem set. When I do this competitive benchmark with different vendors, I normally take a legacy data system that we have, which is used by this rule-based annotation. So you say, if some things are true about a protein, then it has this and this function, and it's interesting for that reason. So that was it's a legacy system. It's actually not so legacy. It's been developed. These rules are available as XML internally, specific proprietary to this project XML, even if it's not proprietary in the financial sense. That is about 1,600 construct queries. When I ran it, I saw 50 construct queries. If you translate this XML rules into Sparkle, you have very large divergence in basic graph patterns. So basically, how many triple patterns do you have in one of these queries? That goes from 20 to 175, most of them being 54. And the vast, bit more than half of them have some form of negation. And then you run this on 10 billion triples or whatever hardware you have available, and see how long does it stay, does it crash the machine, does not crash the machine. And it's been relatively challenging for most of the benefit talks.
Are there systems that can do that?
Yes. Okay. Alan 5.4 can do it. And I'm going to test virtual example 1 soon and see if that will also work quite nicely. But the nice thing about taking an XML form and recompiling them into Sparkle forms is that you can look at the same query that is semantically equivalent on this data set, but use different ways to express it. So for example, minus or not exists, you have nearly identical semantics in the Sparkle standard. But in our database, in our queries, we are actually given identical results. And you don't know if a database vendor has implemented exists or minus, have given them optimizations, if it's one or the other. You don't really want to benchmark just one which happens to have optimized the query pattern that you use, if the other one might have given you superior performance. The same is true for our case, often using unions or values. So we can either express something with a union, give the example later on, or you can do the same with the values clause. And you really want to see if you can find the optimized form for some of these queries. On some of the hardware, it actually makes no difference how you query. It will always give the same kind of query time. For other ones, it really makes a humongous difference. Makes run in seconds or days, basically.
I have a question. When you say make sure queries match, what exactly do you mean? That you express them in an equivalent manner, so you get exactly the same result, right?
Exactly the same results. So on this data set, this query will give the same results, and they're guaranteed to do so because of the way the data is structured.
But the thing is that if you want to do that independently of data set, you cannot. Like you fix the data set and you say, okay, for this data set.
For this data set, these
but this
queries
has a kind of a, you might bump into an issue there, because if the data set changes, the same data set changes by an update, it might change in a way that at the end you're not going to get the same result. So it's not going to be a correct query actually.
No, but for benchmark, when you fix the data set, then you kind of can express these kind of things differently. And in practice, minus or not exists can give extremely different results, especially when you remodel your data. But often you can give very equivalent query plans for how they actually get executed. So it's definitely fixed on the data, then you can do different queries to see if you get the same results.
So you cannot come to a conclusion and say that, for instance, engine X for this kind of data is, engine X for this kind of queries for minus or for not exists performs or doesn't perform, because it fixes like on a data set.
It's for this use case.
Okay.
So for this use case, these two are equivalent. So if the database is very good at doing the minus, but it's very, very bad at doing the exists. For my use case, I'm quite happy to go along with the minus, and I'll have to migrate my queries along with that, knowing it. But I know that with the minus I can do in 5 minutes, and if I have to do exists, it will always take 2 hours. This kind of things happen.
Yes.
This is not so much the case in the union of values. These are really equivalent semantically. Values gives more options, but in the format we use them, they're definitely semantically equivalent. And again, like I said, these kind of databases have really large differences in what is optimized and what is not. This is another example of the queries. It's actually the first one. All these queries can be expressed as construct queries, or they can be expressed as select queries. Here I expressed them as select queries, which is good for this benchmark because you want to avoid the overhead of the data transfer from the client machine to the machine it runs on, because the data that actually gets generated by these queries can be significant. So if you're using something with Oracle and an InfiniBand connection, you just get 40 gigabytes per second data stream coming in. It doesn't really change the query execution time compared to the Alum system where we use 1 gigabyte per second HTTP connection, for example, or the Eureka XMT machine where you have local super high speed connection between the query node and the execution machine. You want to avoid this. So just sending over a minimal XML or a JSON output where it just does the count kind of avoids taking the bandwidth consumption into consideration. So they're all valid Sparkle 1.1, and most of the databases we test support all Sparkle 1.1. Always small, tiny bugs. For example, Oracle 12c didn't recognize the false option there. You had to write out a complete false boolean. Eureka doesn't have the path queries yet when we tested it, so we have to materialize the entire taxonomy trees, and this will also make performance differences. So we have tested all these little variations with materialized, not materialized path queries, bound or not bound, values, units, exist minus, and really see what's good for us. And this is quite a normal one. So we say we want the field patterns to be true. This protein has to have a certain set of domains. It must not have all of these other domains, and it must belong somewhere in a certain taxonomy. So the same query for our data set can be also be written like this. Replace all the union values, replace the filter not exist minus, and all these permutations I have available.
This is a spin thing?
This actually, I actually have it as spin syntax as well.
Yeah.
And this actually comes out pre-colored by Top Right Composer.
Yes.
So I use that quite a lot.
But it lives on a class, some classes then, yeah?
Actually, it lives on the UniProt protein class.
Okay.
But in practice, I'm just executing Sparkle queries. There's no string involved. It's just I have the string rules, mostly for being able to refactor them automatically.
Yeah. Propagating.
Yeah. And so some of the differences is that, for example, RDF type, non-protein RDF type happens 2 billion times in our data set. A protein happens only 56 million, so these different entities happen at very different times. Here you have a path query, RDF has subclass off, that expands to 1 million nodes, so that one entity builds up to 1 million taxonomy nodes. And just to give an example of how that kind of complexity adds to it, if you materialize this RDF subclass of relationship, for example on Virtuoso 7.1, on a 16 gigabyte nice workstation, that takes 10 minutes to just do that one. Alden, very similar, same sort of speed. So just that kind of added or materialized or not materialized subclass of relationship really changes the entire performance picture of such a query. So some of the hardware and software that we've tried, it's all qualitative. Mostly because the really nice hardware I don't get to keep. I get to test it once, I get to make their developers upset, and then they take it away from me. Maybe I should stop making them upset with me. But out of 5.2 and 5.4, which is actually what we now use, 5.4 is a bit faster, I can read on the complete text. But it completes the tests. It takes about 20 gigabytes of Java to do so. But this is on a machine which has two very slow spinning disks. A 64-core AMD of 2 generations back. We also tried Eureka from York Data. This is a machine hosted at the Swiss Supercomputer Center, which has a really nice 2 terabytes of RAM. It doesn't implement everything with Oracle 1.1. And we also tried Oracle almost 12c on Exadata. Quadrant node, 18 terabytes of flash, really quite nice. Our experience with this machine was that it tended to crash out of memory. So having an in-memory database is very good. Even if it's 30 terabytes of RAM, you can still run out of it. So that's really a software quality issue. And that's actually something that's quite crucial for benchmarking is the solution has to pass the benchmark. Not completing the queries is basically infinite runtime, therefore it's disaster. Oracle was kind of more interesting on 12c. It was quite happy to do loading, really fast. Like I said, 18 terabytes of flash disks and really PCI flash, fantastic performance. And then we started running the queries, and Oracle Cost Optimizer said, this is too complicated, I'm not doing anything. So you have Oracle Exadata 128 4 CPUs, fantastic infinite band connections, and basically it only did one thread, most stupid possible imaginable direct translation of the query plan and refused to optimize it at all. So hardware and price don't always predict performance. That is one of the key takeouts of what I've really found. And other thing is performance changes drastically over time. Bugs get fixed. Bugs, when you get fixed, completely change performance because optimizers start working, or well, you remove memory leaks so things pass. And in the end, slow but sure wins the race. Aulim is not the fastest of possible combinations, depending on the amount of budget you provide it, but it is consistent in that it works, and that's really nice. And when it fails, it's quite specific about it. While it fails, it was, well, you didn't order by all your 12 billion triples in memory, and that didn't really work with a subquery in that case. So it's very clearly why it works well. For other ones, you have very trivial queries, should have worked very well, but somehow you materialize everything into RAM, and away it goes, and then you need to go and call some sysadmin to reboot it, which is not so nice. The Oracle Exadata is a bit worse. It's, let's talk to some people at Oracle and say reboot the machine. Chocolate time?
Yeah, if you're right, but that means something else.
Yeah.
Negative chat.
Oh, sorry. So some of the systems to test again are virtual 7.1. I've been enabling it. It works. I just need to get the hardware. Now we finally got the new hardware to see how it's doing. Big data. It's time to retest it. The last time we tested it, it finished loading. I'm mostly looking at the open source cluster supports, which for other solutions, unfortunately, is payware, and we're for academics with, like I said, access to toys, but we can't keep them. So that's the issue.
It's possible to have these. Okay, the dataset is downloadable, but the queries.
I can send. I can send. I can have to regenerate them for the current dataset, but I can send it to you.
That would be very nice. I mean, we run that before you do, so you do the same thing in trouble because we do query optimization all the time.
Yes. So yeah,
There are 1250 of them.
yeah, that's how the Oracle guys started as well. I'll just optimize it. And by number 5, he was looking at the file and said, how many more do you have? Well, you know, another 1200, and then times 6. It's which is good because, like I said, it really figures out what is the software capable of, which is for this kind of compile or optimization is just a requirement.
Yeah, sure. But OpenFacts does also use your data, and we are bound to have all the same patterns, so it's not like 1,200 distinct tricks that you have to do.
No, but it's benign as it exists, and bottom facts only have one-eighth of the data volume, so it's changes. Not similar hardware that we have actually productions that have changes, big things. You can ask me questions now at dinner, or on Twitter, or at Answers Semantic Web, where I have this pink robot. So feel free to ask me questions.
Okay. Well, I think we should go definitely for the dinner option. We'll talk about this later. But give Jerven again a hand.